Okay, hello everyone. Gernot has just talked about the main goals, principles of LionsOS. I will be talking more from a developer's perspective and concretely what have we been doing for the past year. So, I'll give a brief introduction of the overall design of LionsOS and its fundamental parts. I'll talk about what progress we have made in the last year and some of the more unique problems to LionsOS that you might not find in a typical OS. And then at the end, I'll do a demo. So, one example system of LionsOS might look something like this. You've got your hardware, you've got SEO4, and then this blue box over here represents everything within LionsOS. So we've got the SEO4 Microkit, which is the foundation of it that controls access to SEO4 rather than we're not dealing with direct access to capabilities and that kind of thing if you're a client or user of LionsOS. And so depending on your system, you might have some I/O subsystems. So maybe you've got graphics for rendering a UI or something. You've got some networking. You've got a block subsystem that's connected to a file system. And then you might have like a legacy client that you're running in a virtual machine or something like that. It expects an environment like Linux. And then you've got any number of clients. Okay? Now the thing is that we're not telling people exactly how to set up their system or what components they require and so on. So we have some preset I/O subsystems. That's to do with STDF, and I'll go into detail in a bit. But it's up to the user for how they want to construct their system. So the system design is very involved. You might have some basic networking, but maybe you have some higher level components like a firewall or something, depending on your use case, right? The whole point is that LionsOS provides you these components, and then it's up to you to figure out how you want to put them together, right? And these are all isolated, so it's up to you. If you want a client to be able to access the file system, then you always explicitly give it access. There's no kind of implicit resources or communication between all these subsystems, okay? I'll talk a little bit about the Microkit, which is the foundation of this. I've talked about it in the past, so I won't go into too much detail. The main things you need to know for LionsOS is that the programming model is event-based, so every LionsOS program that you write will be event-based as well. There is asynchronous and synchronous communication. For most of the LionsOS components, we heavily rely on asynchronous communication for performance, but there are some cases where synchronous is the much more obvious solution and doesn't necessarily degrade performance. And so Microkit provides the interface to SEO4, and it lowers the bar to SEO4, but it does not include things like drivers or higher level OS services, right? So that's what LionsOS builds on. Okay, I'll give a brief status update since I do most of the development on Microkit so far. And there's been a couple releases in the past year, and most of the effort in the past year has been on just kind of catching up and giving people the requested features they've been asking for. So things like hypervisor/virtual machine support, other architecture support, so RISC-V is merged in, x86 is still in progress. It's definitely on our roadmap though. More platform support, various fixes and quality of life improvements. So now I will talk about one of the main parts of LionsOS, which is how we do I/O. So like Gernot said, I/O is based on the SEO4 device driver framework, and it's designed for radical simplicity, performance, and modularity. So the general pattern you'll find is something like this, where you'll have your driver that talks to the device. It's only concerned with converting STDF protocols to the device interface and nothing else. And then you have the virtualizer that would be responsible for multiplexing clients and dealing with how to share the device, and any other things like address translation if you have a DMA-capable device. And then you've got your client on the left, right? And all of these tend to share some kind of transport layer for handling requests and responses and that kind of thing. It varies a bit depending on the device class. We do a design from scratch for every device class, but this is just the general pattern. And so these LionsOS components, they sit on the left of the virtualizer. So if you had a file system, that would be consuming, an SDDF block subsystem and then converting it into some kind of higher level LionsOS API like for file systems, right? Because you don't want to, if you're a client, you usually don't want to work on the block level. Same thing goes for like networking and so on. Okay, so last year we had a fairly mature network system and we had basic timers as well. In the past year, we've added a number of other device classes. So we've got block devices, so for MMC cards and NVMe devices that we've been working on. And we've got UART, just for basic logging and that kind of thing, I2C, and audio as well. We're also working on a bunch more, like 2D graphics, GPIO, pinmux, clocks. So far, pinmux and clocks are becoming more and more important as we have more complex systems. So far, we've just been relying on whatever the bootloader does to initialize the system and do all the pin control and that kind of thing. And so now we're writing native drivers to do that as well. So that's the SDDF side of things. In general, like I said, anything to the left of the virtualizer is part of LionsOS itself. So SDDF is not responsible for providing a file system or any higher level components. And so, like I said, a file system would be part of LionsOS. And so to illustrate the difference, here on the right, I've got an SDDF block subsystem. So it's got the block virtualizer, an MMC driver if I'm talking to an SD card. And then say if I've got two clients, I've got a file system for each of those, and the block virtualizer would be responsible for actually managing the partitions of the device. So we can ensure that this top client can't actually talk to the same partition as the other client, so they can't mess with each other. That's what the virtualizer is supposed to enforce policy like that. And so the past year, we've mainly been focused on doing these SDDF I/O designs, and now we're moving towards the higher level, like file systems or socket APIs, that kind of thing. So another aspect of LionsOS is virtualization support. So I touched on this a bit last year, but for enabling legacy clients as well as virtualized drivers, which I'll talk more about in a sec, we use virtualization. And so last year at this point, I think we basically just were able to boot simple Linux VM on AR64. Now we've added a bunch of VirtIO device implementations for console, block, network, and audio. So this allows, if you have some kind of VM, it can now talk to the rest of the system and actually do I/O, and it's a bit more useful. RISC-V support is now working. That's based on Yanyan's kernel changes, though, which are years old at this point and haven't been upstreamed. So I'm working on finally creating an RFC for that and upstreaming them. And multi-core guests are another popular aspect of virtualization that we're also working on. So one last thing I want to touch on about the design is that while we have a static architecture, so when you build your system, you know how many components you're going to have, you need to know what resources they're going to use, where they can communicate, and that kind of thing. That seems to make people think that when you set up the system, you deploy it, that's it, it's done. You can't touch it anymore. If you want to change something about it, you got to take the whole thing down, redeploy it, right? But there is obviously a spectrum to this. We might never get to the point where you can hot plug RAM or something like that, but we can bring in more dynamicism to, for what people expect. So there's a couple of things we're doing to address this. One of them is introducing hot plugging to SDDF. So for example, you can now eject or insert MMC cards into a live system, and then the system should still be able to respond to requests and work. We haven't done it for any other I/O subsystem or device classes yet, but that would be the obvious, like the next point would be probably networking, be another one. And Another point is the template protection domains in Microkit. So what this means is that you may not know or you may not want to deploy every single program that's going to run when you start or when you initially deploy a LionsOS-based system or a Microkit-based system. And so you might have some set of resources that the program, when it's loaded, maybe sometime later down the line, it will use a strict subset of those, or it might use all of them, but it depends. And so we're working on a way of, at runtime, being able to look, encode into a program what subset of a certain amount of resources it's going to use, and then strip those away by a trusted loader, and then start the program, right? So it adds a bit more dynamicism. Okay, so that's the basic design part of LionsOS. I'll now talk about what have we actually concretely done with all this. So we have a reference system, which is also called the Kitty. It's over there by the coffee machine. You can try it out. It's basically just a point-of-sale system that uses quite a lot of the I/O that we've implemented so far. And it was basically just a first kind of real, semi-real deployed system that we use in our lab that we could test out LionsOS and how does it actually work to put everything together, right? So it's mainly to give us feedback, as well as for newcomers to LionsOS to give them an entry point to see how do they properly design a system on LionsOS, okay? And we've also made a web server, which is using a lot of the same components from the Kitty, and that now, I think as of yesterday, officially hosts the SEO4 website. So if you go to that URL, you will actually be using our web server. So I'll talk a bit about the Kitty system. You can see that we've got all sorts of I/O, so I2C to tap cards. We've got Ethernet to talk to a network file system, as well as an external server that holds some database information, and serial and timer. We've also got a VMM that is responsible for exporting a frame buffer. So we don't have a native graphics driver yet, but we still can draw to the display via this exported frame buffer. So this is an example of a virtualized driver VM. And to hook all of this up together, there's a client program running in a MicroPython interpreter, which is just a stripped down version of a full Python interpreter intended for embedded environments. And so we've been using this to experiment and that kind of thing. So what did we learn from doing all of this? Well, it's still too hard to put everything together. When you're dealing with these STDF I/O subsystems and that kind of thing, there's a certain amount of memory regions you have to have mapped in. You need to know exactly where the device registers are for the drivers. You need to know the correct mappings and how each component will communicate with each other. So those are all standard and they're fixed. They can't change. There are some parameters that you can change, but that means that a lot of the time you're spending a lot of time fiddling with these kinds of things, and it can be kind of fragile. So with the Kitty example, we have 3 or 4 different I/O subsystems, and it's already getting, there's a dozen components, and it doesn't really scale well. So we need to address that. Another point I wanted to make is that with a static architecture, some of this runtime complexity that you might find in Linux, so do I have access to this device and so on, what drivers do I need to load and that kind of thing, that complexity is shifted to the build time in LionsOS. So we also need to do something to address that. And the general comment I want to make is that when you say, okay, we're going to have a new file system interface, we're going to have a new, whole new different way of doing I/O and all these OS services, you are going to push the friction higher and higher to the point where people are not going to bother with it, even if it's verified, even if it's secure, even if it's performant, right? So you need to do other things to compensate for that, right? And so now I'll talk about the couple different approaches we have for lowering this friction that we encountered. So one of them I showed an already example in Kitty of we did when we didn't have or didn't want to write a native graphics driver. So we used a pre-existing driver in Linux and encapsulated it into a virtual machine. And obviously, you wouldn't want to always do this for every single driver, but where the concessions to performance and security are acceptable, you might want to do this to make it faster to develop. And the end goal of these driver VMs I would like is to have it really easy to prototype a system. So say you're new to LionsOS, rather than sitting down and having to write a bunch of drivers from scratch before you can do anything useful, you should be able to, for whatever platform you're targeting, have your client program spin up a number of driver VMs and then iteratively convert those into native drivers, right, for the ones that matter to you. So what these driver VMs do is they still talk STDF, and now they convert whatever the protocol or interface is for the specific device class to either Linux system calls or Linux libraries. So this is done via something called the user I/O framework in Linux. It's just user space I/O. So if we look at the diagram, it has the same kind of structure. We've got a client, which talks to the virtualizer, and then that talks to the driver. And from the client's perspective, this is completely transparent, right? And that's really important because I want to be able to transparently just take away that driver VM once I've finished writing a native driver and put it in and have everything still work, okay? And yeah, so these UIO drivers live in user space. We don't modify Linux. We don't patch Linux at all or have any kernel modules that we install. They're purely in user space. One of the problems with this is when you want to have, say, an Ethernet driver VM, right? You don't want to write a native driver, so you have a driver VM for it. It'll try to access the Ethernet device, obviously, but it'll also try to do stuff with the clocks and the pin marks. And obviously, you don't want this. One, because you don't want a Linux VM controlling this kind of stuff because it affects the rest of your system. And two, it means it's impossible to have multiple driver VMs, right? Because if you have two Linux VMs, say one for Ethernet, one for SD cards, you can't have both of them accessing the clocks. And so that's another use case for our native clock and pinmux drivers where we trap and emulate accesses to these clocks and pinmux devices. To my knowledge, there is no standard way of doing this kind of emulation. When you have something like VirtIO, there's standards for emulating an Ethernet device or a block device or serial device or something like that. To my knowledge, it doesn't exist for clocks or pinmux. So we have to do this per platform. It's not very generic, which is one of the negatives of it. So one of the things when you make a Microkit-based system is that you use a file called like a system description format file that you give to the tool, and that tells you, okay, I want this many components, I want them to have this memory, I want these interrupts, these channels between everything for communication. That, like I touched on before, becomes very finicky when you have lots of these components. And from the initial design of the Microkit, it's always been intended to auto-generate this kind of stuff. And so that's what we're working on as well. Another aspect of the complexity with moving some of the runtime complexity into build time is information flow from the design of the system, which the user decides, to components that LionsOS provides. So if you think about one of the virtualizers for an STDF device class, you need to know it needs to know how many clients does it have, for example, and that is something the user can change, but you don't want the user having to change the code and that kind of thing. So a general problem we have to solve is how do we deal with this kind of information flow? And so I'm working on various tooling to deal with this, and we're starting to receive internal use of it, and hopefully this will be usable by other people soon. One of the tools that we're working on is a GUI visualizer editor for these system designs. So this one is the kitty. That's how it looks like when you draw out all of its connections and components. And this is using the same kind of low-level tooling that I've developed, so that if you want to make your own tooling on top of it, or if you don't want to use the UI or whatever, you should be able to do that, right? I want to give people the ability to create their own tools on top of this, right? And so if you come to my tutorial on Friday, you'll see an example of this being used. Okay, the last aspect of lowering the friction is this legacy layer that Gernot touched on in his talk. We don't have any legacy clients that we're using with our example systems, but we do have some off-the-shelf libraries. For example, our network file system expects certain POSIX like APIs, like Socket, the Socket API and that kind of thing. And so we obviously don't want to implement all of POSIX or the whole standard of it, but we do want people to be able to take off-the-shelf libraries or legacy clients and fairly easily port them to LionsOS. And so, commonly you'll see things like blocking I/O calls for read, write, send, and that kind of thing. But we're not implementing, fork or exec or any of these kinds of things. Okay? And so to give an example of how this legacy layer would look like, I've got another typical example of the fat file system being used with the block subsystem. All of the communication is still asynchronous, and all of this legacy layer is encapsulated in the client completely, right? We're not designing, two interfaces, one always for asynchronous, one for synchronous, right? The implementation of the LionsOS components and SDF always stay the same, but it's up to it's the client code that's actually making it look like it's synchronous communication. Okay? So my last point is a demo. I said at the start I would give a demo, but I have lied. The demo has largely already happened. On the left, there's a small ARM SBC, single board computer, that's got a battery attached to it. On the right, I've got an architecture diagram of a system that has native serial, just for output, for serial logging, sorry, and a native network subsystem that's talking to an Ethernet device. I also have an Ambient-based Linux guest that's using those devices via Video Network and Video Console. And it has some pass-through access to the graphics and USB and the SD card. The system is running my slides right now. You can see here, if I lift it up, I have the system running right now, and it's showing you these slides. And so technically, I can say, well, I will not lie, the guest is doing a lot of work. But we have some native components, and it means that technically that my talk on LionsOS has been delivered on LionsOS itself. That's all I have.
Okay, thank you. Questions?
You mentioned briefly the desire to auto-generate the SDF.
Yeah.
Can you say more about what that stands, or where that stands, or what the input to the generation would be?
So it's just, so yeah, that's
what would users have to provide?
So one of the things that I think most people would gravitate to is some kind of configuration language. In my opinion, this would end up evolving into something that just looks like a programming language anyways. And so what I've done is just created just a simple library that you call into with some kind of meta program, whether it be a Python script or a C program or whatever. In the case of the GUI tool that I showed, it's actually via WebAssembly calling into that. And it's just some JavaScript code that's generating the UI. And so it's just code. There's no configuration language or that kind of thing. Yeah. So it's what would be a 300 or 400 line SDF file for the kitty, for example, is maybe 40 lines in like a Python script to auto-generate it. Yeah. I'm still yet to figure out how to do the information flow, but that's how the SDF is generated. Yeah.
Okay, we have time for more questions. Okay.
Yeah, thanks. Great talk. So I have a pretty engineering question. So it appears to me that when I look into the Microkit script, it seems to emulate the booting process of SEL4 to figure out the capability table.
Yes.
Well, at least the Python version, I haven't looked into the Rust version after that rewriting.
Yeah.
So I only noticed that because I found some discrepancy with that emulation and the actual booting process.
Okay.
So I'm thinking like you are doing the same thing twice, but there may be some discrepancy there. So is there a reason why you do that, or like do you have any comment on that?
The reason for that is to be able to statically reason about how much memory do we have, where do we put all these kernel objects in memory. We don't, the current approach is not to figure that out in the initializer program. So it means that at build time, you know exactly where everything is going to go. And again, because it's a static architecture, you can do that. So while there may be some discrepancies, that's a bug, and I would like to know about it if there was one. But again, this is something that would be caught at build time rather than runtime in some kind of initializer. The eventual goal would be to move to something like the verified CapDL initializer that would have more assurance than this build tool, but that is not the current case.
Great talk. I think something that could be helpful is a rough roadmap of, especially with a timeline,
Okay.
when you expect some of those things that you have laid out for future.
Which was there things particular, or did you want an overall?
Well, personally, x86 support, but
Okay.
any of them, just like I don't need it today, but I
Right.
mean, like if there's a place that you can look at online.
We will post a roadmap to the website LionsOS.org. I hope to. There is one right now, but it's a bit outdated. I hope to keep that updated. The timeline for things, it varies a lot because every couple of months something else comes up. So yeah, but x86 support, that is something that various people from various groups have requested. So that particular, I would like to have that within the next 2 to 4 months. Yeah.
Okay, so one last question.
So I wonder what's the performance, the overhead of using Linux VM as drivers in terms of performance and resource usage?
Yeah.
Any idea?
We have only done benchmarking. So something I forgot to mention in the talk was we have we have driver VMs for 2 device classes right now. We have it for block and for audio. The benchmarking that we've done for block has been pretty minimal. We've only done it for SD cards, which are, they're only like 10 to 30 megabytes throughput maximum, and they're not, I believe, particularly interrupt heavy, unlike networking. And so I don't have exact numbers, but we've done a bit, and the degradation was not too bad from my memory. But I would like to do a lot more. For audio, it's very low throughput, and what you're mainly concerned with is with latency. And from what I remember, the degradation was maybe in like around 5%, I think. But I would like to properly go through each device class, do a driver for it, and then benchmark it properly. That's something I'm intending to do.